Remember the convert from radical to exponential form, you are changing it typically to a fraction. Your denominator is the index, and in this case, the index is 2. They rewrote this. I mean, you could say 27 to the 1/2. That's the same thing as 3 cubed, right? So they just rewrote this 3 cubed. So that's how this one became 3/2. These are your numerators. So that's why A became 4/2, which is 2, and B became 3/2 as the exponent. The exponent on the inside is your numerator. The index on the outside is your denominator. They tell you here that pH is measured with logarithmic functions. They use the scale of pH as a logarithmic function. I just found this interesting, how acidic. It's more acidic than, did you see what it's more acidic than? In your stomach, right? That's more acidic than your stomach. So when we start talking about logarithmic functions, the way that it relates to inverses, which is what we've been doing, is the logarithmic function is the inverse of an exponential function, which means they undo each other. Think about addition and subtraction. If I add 3 and subtract 3, I did not change anything. They undo each other. And so log functions and exponential functions undo each other. So the first thing we're going to talk about is what a log function looks like. Normally our brains can conceptually understand exponential functions because we've been doing exponents since like middle school, but logs tend to throw us off, and we just need to think of them in terms of exponents. So look at how they have defined it and then how we write them. A log function, assuming that b and x are positive numbers and b does not equal 1. Y equals log base b of x if and only if x equals b to the y. So what does this mean? My exponent. In a log function, the exponent is actually what you're solving for. That's what your log function equals. You're saying, what exponent do I take this base to the power to get this number? So you'll notice my exponent here in my exponential function is actually what I'm solving for in a log function. The bases are the same. So the base of the log function represents the base of the exponential function. And then the number of the log is actually what we would solve for if we were given an exponential function. And we're going to do some of these. So if we were going to rewrite this, let's say we have some number, 27 equals 3 cubed, or 8 equals 2 cubed, right? So something that we know, 8 equals 2 cubed. Everybody would agree with that. How would we write that as a logarithmic function? Well, we would say log of the base is 2. So log base 2 of 8. What we're asking here is, what power do I take 2 up to be equal to 8? That's what they're asking. What power of 2 do I have to raise this to get 8? Well, that power is 3. And so you can see how they convert. 2 cubed equals 8. So log base 2 of 8 equals 3. These are inverses of each other, all right? Logarithm, think of it as just another way to write an exponent. You're just looking for different things. With an exponential function, you're saying some base to a power equals a number. With a logarithmic function, you're saying the log of some base to a power is this number. I need to find the power, all right? And so the first thing we're going to just do is rewrite them. If I wanted to rewrite these in exponential form, they've given me log form. I'm going to rewrite it saying, well, what is my base? My base is 5. What is my exponent? This represents the exponent. What does all of that equal? That's that 125 there. Next one, what's my base? Well, my base is 3. What is my exponent? Exponent is 1. 3 to the 1 will equal this number right here. All right, let's look at the last one here. My base is 10. My exponents can be negative. That equals 0.01 or 1 over 10 squared if you remember your exponential properties, all right? We can go the other direction. Let's look at this first one. They want us now to write them in log form. So we're going to say log form, start with the log. What is my base? It's the same base as my exponent. That is 2. Now we're looking at what it would equal, 16. And now our answer is, what exponent do we have to take 2 up to be 16? Well, that is going to be 4. Let's look at the next one. My base here is the same base, 10. What do I have to take 10 up to get a 1? Well, I have to take it to the power of 0. Last one. Log. My base here is 2. 2 to what power equals 1/8? My answer here is -3. So a couple things I want to point out. One, the log of any 1. So log of any base of 1 is going to be 0. Why? Well, because anything to the 0 power equals 1. All right? If I have a base and a fraction, you're going to have a negative exponent because that's how you get a number into the denominator, is using a negative exponent. Okay? One thing they didn't give me here, if I had something like this, log base 16 of 4. What power do I have to take 16 up to get a 4?
No.
It's actually a square root. I can write a square root as a power. How do I write a square root as a power? We just did it in bell work. If I want to write the square root of something in exponential form, how do I write it? It's something to what power?
2 to the power of...
So 16 to the 1/2, that's the same thing as the square root of 16. That equals 4, all right? So if you get a number that is smaller, 16 is bigger than 4 here. And I'm saying I have to take 16 to a power to get 4. You're likely going to have a fractional exponent here. If you have a base and a fraction, and you can see, well, I can take 2 to the 3rd power to get 8, then to get 1/8, I'm going to have a negative answer here. All right? So I want you to try some just rewriting. All you're doing is rewriting. Rewrite the first 2, convert them to log form. The second 2, convert them to exponential form. So you're making these look like that, and you're making this group look like the first 2. So if you want to evaluate something like this, the easiest thing to do is say, well, that is going to equal some number that I need to know. And again, your brain doesn't typically go to logarithms. So if you rewrite it in an exponential form, it will make more sense. So if I were to rewrite this, this is my base. This is my exponent that I'm looking for. And that is what all of it equals. All right. So now I'm going to say, what power do I take 3 to get 81? So what power do I take 3 to get 81? 4. However, I want 81 in the denominator. So how do I tell it in exponential form to put it in the denominator? Negative. So x equals -4. All right? And so it's easier in your brain to convert it to exponent and say it makes more sense because I've done exponents for so many years, right? Logarithm, and you'll get to where you can look at it and say 3 to what power equals 1/81, -4. But if you need to, you can rewrite it in exponential and say, okay, what's happening here? All right. The other thing you can think of is I may be able to rewrite it to the same base. 3 to the x equals, and rewrite this with a base of 3. That's 3 to the -4. All right. If my bases are equal, then that means my exponents must be equal. All right, and so when you do it this way, you can also just go ahead and drop down and say, well, x must equal -4. All right, any questions on that? They are saying 2 to what power equals 8? So 2 to what power equals 8? What is x here? 3. All right. 5 to what power then equals 25? There we go. What about this one? 2 to what power is 1/4? -2. What about this guy? 9 to what power equals 3? Yeah, 1/2. All right. Does that make sense? So look at it this way. If I rewrote this as a 3, that's 3 squared to some power, right? Which is 3 to the 2x equals 3 to the first power, right? 2x equals 1, x must equal 1/2, all right? So you can think of it two ways. You can say, remember, anytime you're taking something to a power and the numbers are getting smaller, you're likely taking a root, right? So what root is it? It's the square root. We rewrite square root as 1/2. And this is why. This process is why. So I'm trying to get 1/2 to raise to a power to get 32. If I multiply 1/2 times 1/2 times 1/2, I'm going to remain a fraction, right? 1/2, 1/4, 1/16, right? I'm going to keep going up. So I really have to flip this. So I set it up this way, 1/2 to what power equals 32. And then I rewrote them both as powers of 2. So if I rewrote this as a power of 2, that's 2 to the negative 1. If I rewrite this as a power of 2, that's 2 to the 5th. So negative 1 times x, so this exponent will equal this exponent. And then I just solved. So in your calculator, you have 2 logs. We're going to only deal with the first one. You actually have one that says log, L-O-G, all right? That is a specific log. It is a log base 10, all right? So anytime you use that log button on your calculator, your base is automatically 10. It's called a common log. So anytime you see a log with no base, you have an assumption that it is a base 10. Just like when you don't have an exponent, you assume it's an exponent of 1. When you don't have an index on a radical, you assume a square root index of 2. When you do not have a base on a log, it is an assumption common log base 10. So in your calculator, if you plug these in, it is telling you 10 to some power will equal this number. So these are going to give you nice, pretty round numbers, right? 10 to what power is 100? Hopefully you can do that. That's 2. 10 to what power is 1/1,000? Negative 3, right? So when you plug these into your calculator, you're going to get 2. You're going to get negative 3, right? Here we're going to get a little bit different because 10 to a power does not equal a perfect 30. So this is going to give you a decimal. All right, so go ahead and try this in your calculator. Try those first 2. Make sure you're doing it correctly. For your larger calculators, you're going to do log and then input your number. If you have a smaller calculator, you may have to put the number in first and then hit log. It depends on what your calculator does, all right? So try those first 2. You should get 2 and you should get negative 3. All right, you should get 2 and you should get negative 3. For C, you're going to get a decimal. Logs are typically rounded to 4 decimal places. 4 decimal places. So in your calculator, when you do log of 30, you're going to get a long decimal. You want to look to the 5th one and then round the 4th decimal place. So you get 1.47712. It keeps going. You're going to look at this. It's below 5. Keep this the same. So your answer is 1.4771.
Why is it off?
For D, I'm technically going to a fraction. All right? So you probably should get a negative number here. So when you put this in, you're going to round it. It's going to be, when you go in your calculator, negative 0.522878. It keeps going. Look at the 5th place, 7. That is more than 5. Go up on that 8. So negative 0.5229 is your answer there. Some properties of logarithms. This is going to help us start using logs to solve equations, all right? We've already talked about this a little bit with exponents, but this is also true of logs. If you have the same base, two logs equal to each other with the same base, you can assume that what you're getting the log of are also equal. So this is true if and only if those two are true as well. So this equals only if the x and y equal. Just something that you can use when we start solving logs. Properties. There are going to be times when you want to expand a logarithm. You have the log of some group in here, and you want to break it up into individual logs, all right? Think about my exponent rule. When I multiply like bases, what do I do with the exponents? I add them. So for logarithms, if I have two things being multiplied, I can break them up with addition. This falls from my exponent rules. Division. When I divide like bases, what do I do with my exponents? Subtract. So if you have a division within a log, you can break it up into two logs by subtraction. All right? Power to a power. What do I do with my exponents when I have a power to a power? I multiply. For logarithms, your exponent can multiply in front. So you can take the exponent and pull it out in front. All right? You can go both directions. If you have a single logarithm, you can expand it into individual. If you have individual logarithms, you can condense them into one. All right, and this is going to help us do some solving. So let's look at just expanding and condensing. All right, so let's look at this. They want us to take these and put them into one logarithm. So we're going from multiple and we're putting it into one. All right, this is subtraction. What exponent rule deals with subtraction? Multiplication, division, or power to a power? Division. So that means we are going to divide. We are going to condense this by saying log base 2. Don't forget your base, because remember, if you don't give me one, you're telling me base 10. This is base 2. We're going to say 32 divided by 8. We can simplify that. What is 32 divided by 8? So that is log base 2 of 4. Which we can actually solve, right? We can actually solve that. We could solve it individually or we can condense it and solve. They're just wanting us to condense. They're not asking us to solve, so this is the answer. All right? Let's look at the next one. We have multiple things going on here. We are multiplying and we have an addition. So we're going to deal with this first, all right? Anytime you have a coefficient, that can become the exponent. So this first step, we're going to rewrite this to x cubed. All right? And then which one dealt with addition? Which base property deals with addition? Multiplication, division? Yeah, multiplication. So now we can rewrite this to one log. Log, our base is b. We're going to say x cubed times y. All right? So we can condense into one logarithm. All right, we can go the other direction. So look at example 2. There's a couple steps here. When you have something like this, you are going to want to rewrite a radical as an exponent. All right, so I am going to take this guy, and the first thing I'm going to do is I'm going to rewrite it as an exponent. Cubic root is rewritten as 1/3. All right, 1/3. Here's the thing. I usually go ahead and take those to the powers while I'm doing this. Because when you expand it, the 1/3 is going to apply. They don't do it that way. So we're just going to do it the way they did it. To expand an exponent, that is going to become my coefficient. So I'm going to say 1/3 times the log base 3 of d squared over c. How do I separate division? What do I do with exponents when I have division? What do I do with them?
Subtract.
I subtract. So I'm going to separate these with subtraction. 1/3. I have a log base 3 of d squared minus a log base 3 of c. I'm actually still not done. This exponent can go just in front of the d portion. So I have 1/3 2 times log base 3 of d minus log base 3 of c. That is fully expanded. If you wanted to distribute the 1/3, you could. You don't necessarily have to. The first thing we can do is if we have estimations, then we can use those to help us get logarithms. So logarithm of 175, if you were to break this up into primes, you're going to get something like this. So 5 squared times 7 is another way to write this log, right? Well, they gave us estimations for this, so we can split that out. We can say, well, 2 times the log of 5 plus the log of 7. And we can plug in what they told us. Log of 5 is this, log of 7 is that. And we can estimate what that log would be. We can do the same thing with something like this. They gave us a 5. This is a common log. We could say that's log of 10 over 5. That's the same thing as 2. And we can say log of 10 minus log of 5. 10 to what power equals 10? Yeah, anytime you have a base and the number you're taking the log of, it's going to equal 1 always. And then we can just plug in what they told us for 5 to estimate this one. So that's one way you can use estimation with expansion. The other way you can solve problems with expansion and condensing is something like this. All right? So remember we said if your bases are the same, then what's inside will equal each other. We just have one problem. We have this 2 on the outside. So what we can do is we can move that to the exponent place. So we'll say log base b of x plus 3 to the second power, log base b of 36. Anytime your bases are the same, what is inside here will also equal. So if my bases are the same, I can completely ignore the log and I can say, well, that must mean that x plus 3 squared equals 36. How do I solve this? How do I get rid of a square? What do I do to both sides?
X plus 3 times x plus 3. Oh, no, get rid of
Right, so that does mean to multiply by itself. If I want to get rid of it, I'm going to do the square root. So x plus 3, we'll get rid of that square. What is the square root of 36 when a variable is involved? Positive or negative 6. Positive or negative 6, which means I need to set up 2 equations to solve this. X plus 3 equals positive 6. X plus 3 equals negative 6. All right, which means x is going to equal 6 minus 3 and negative 6 minus 3. And both of those will give me an answer. Now, just like, by the way, any other of these equations we've been solving, you do have to check and make sure they work. All right? If I plug in a 3, I'm going to get 3 plus 3 is 6. That's fine. Here's what's not fine. If I plug in a 9, I'm going to get log of some number is a negative 6. All right? Here's the problem. If you do log of any base, log 10, let's say, of negative 6 in your calculator, you should get error. You cannot take 10 to any power and get a negative number. So you can't take any base, because those are going to be positive, to any power and get a negative number. It's not going to work. It's always going to be a positive number. It may be a fraction, it may be a number smaller than what you have, but it will not be negative. So this guy does not work. All right? If you plug it back in and you get a negative number for that log, it is going to be extraneous. So this is my only solution right here. So you do have to check these and make sure it's not extraneous. They won't always be. If this was x plus 12, negative 9 would have worked, okay? But because it made it a negative number in there, it did not work. Question.